Okay, so I don't know if you've scrutinized the Blackboard interface. I'd just like to go over this for someone here for the first time. The chat window, and you can actually move this as well. You can grab that and move it around. And these are all the people participating. It's just you and the person with you and then myself. So if someone else joins in, they'll show up here. If you have a question, you can certainly ask it, or you can put it in the chat window, or you can raise your hand by clicking the virtual hand raising icon. And if I don't pay attention to that, because I look at my window here and I look at the chat, but I don't always look at this, so I'll try to be aware of that, but just so you know. I'm just going to talk a little bit about some of the Freefall equations, talk a little bit about graphs and have you do some practice with that, and then we'll do a couple practice problems. So these are the equations that you've seen from earlier in the chapter. If we've got velocity, final velocity, initial velocity, just a generic acceleration, and then this just represents a generic position variable. But when we're talking about free fall, we're thinking about up and down motion. So with up and down motion, we typically think of that variable being y. So to relate, it looks like it's a new set of equations, but it really isn't, because for acceleration, we just have negative g. It's not a very good arrow there. So we're saying that the acceleration is equal to negative g, where g is to two significant figures, 9.8 meters per second, or some people like to say 9.8 meters per second squared. Just to remind you, I actually like saying meters per second because that reminds me of what an acceleration is. An acceleration is a velocity unit per time unit. Where meters per second squared, that looks like it's a displacement unit divided by time unit squared. So it looks like I can find acceleration by doing x over t squared, and that isn't a valid equation. So think of g as 9.8. Every time you want to use 9.8, use g. If you go to the store, something's $9.80, you can say, oh, does this cost g? And they'll think you're a little bit goofy. The negative comes from defining down as negative and up as positive. It doesn't have to be that way. There could be a situation where you might want to flip your axes and have down be positive, but the default is down is negative, and that's what the negative sign here means. And then, pretty self-explanatory, that instead of the generic variable x, it's y. And actually, Jared, if you wouldn't mind muting your microphone, unless you want to ask a question, because then I won't get feedback. I'm getting a little feedback. I'm hearing myself, and hearing myself directly is bad enough. Hearing it through yours is hideous. It's a nightmare for me. And then, of course, x right here as well. So these equations are not new equations. Just wanted to point that out. It's interesting, though, the book, I just copied this from the book. They call this negative capital G. Capital G actually has another meaning. That's from Newton's law of universal gravitation, which we'll get to later. So that's just a little misprint from the book. So free fall, dropping a ball. So here's a person, a lovely cartoon hand model, who drops a ball. And this is data that you can get. So if we assume that the origin of the drop is right here in the middle of the ball, as soon as the person lets go, that instant that they let go and it hasn't even had time to react, that velocity here is 0. And you might want to also think of this as maybe v sub y. Since we're only talking about up and down motion, one single direction, one dimension, you don't really need the sub y, but I like to do that just to kind of remind myself of that. So as the seconds tick by, and you certainly have seen this before, you've dropped something, you notice that it starts out slowly and then it speeds up. So sometimes you have dropped something and then you wanted to catch it again. So you've dropped your keys, you're trying to get into your car, and you push the key into the door, and maybe it's dark so you miss it and the keys fall. Well, because it falls slowly at first, you're able to take your hand from where the keys were and then just quickly move it underneath. It's easy to do that right after you drop your keys. This relationship here is y. It starts from 0 and it's accelerating constantly, but remember, accelerating means it's adding or subtracting a certain number of meters per second each second. So in the first second, or in this case the first tenth of a second, it's not adding very many meters per second. So you can easily move your hand at 1 meter per second, because this is basically what the magnitude is. After a tenth of a second is falling 1 meter per second. That's not much of a problem. If you had a long enough distance and someone was below you, now your car is obviously not going to be 5 meters tall, but if you dropped keys out a window, you could probably, as soon as you drop your keys, quickly move your hands and catch it. But if someone is 5 stories below you and you just yell, "Catch my keys," even if they're standing by the window, they're going to have really quick reaction time to grab those, because the floor below, or however many floors below, 5 floors below, that thing is moving pretty quickly. They're going to be moving their hand 5 or pretty soon 10 meters per second. So notice that each second here we are adding, or I'm sorry, each tenth of a second we're adding negative 0.98 meters per second. So 0 plus negative 0.98 is, of course, negative 0.98. Negative 0.98 plus negative 0.98 is negative 1.96. Here again, we're adding a negative 0.98 meters per second. So we get 3 times negative 0.98, or 2.94. Here we're adding it again, we're adding it again. So when something has a constant acceleration, every tenth of a second we're adding a certain amount of velocity. So every 0.1 seconds negative 0.98 meters per second of velocity. Now, as we do that, the velocity, of course, is increasing. So notice what we're adding here in displacement. So the first time we're adding negative 0.049. So that's about 0.05. Here we're adding 3 times negative 0.049. So this is like 0.5. So here it's a negative 0.5, or 0.05. And so we add another 0.05, 0.05, 0.05, so then we're getting it down to 0.2. Here we are adding 5 of these negative 0.049. Sorry, that doesn't look very good. So the first time we added 1 of those, so 1 times that. Then we added 3 times that. So if we look at this pattern here, 1, 3, what are we going to add here? Yeah, 7 times 0.049. So that's obviously what the pattern says, and you can actually see if that's going to work. So 7 times that, and so on. So we're adding the same amount of velocity. So each tenth of a second, we're adding the same amount of velocity. Here, every 0.1 seconds, we're adding, and my verbal skills are not good enough to describe this in just a few words to precisely describe this pattern, but that's okay, because the important thing is to realize that we're adding more and more, so not just more, but more and more to the displacement. So by adding the same amount to the velocity, that means every tenth of a second it's moving more meters per second. So if it's moving more meters per second, it makes sense that it's going to be moving more meters. That was pretty insightful. Maybe I'll write that down. So that's the good thing about these. I can pat myself on the back. Oh, I can do that on camera too. So every 0.1 seconds, we are adding actually, I'm going to change what I said there a little bit. We're adding meters per second thus we must be increasing the number of meters added. Obviously, we're not locked into meters as the unit. It's just that this example was meters. So I have a question then. So that's just sort of conceptually looking at the numbers. So my question is, what would the graphs be? So what would the y versus t, v sub y versus t, and a versus t graphs look like? That's a question, so we probably should be ending with a question mark. Yeah, so what would those graphs look like? So yeah, Jared, if you want to try to verbalize it, the world will hear.
Y versus T would be a parabola, half of a parabola.
Oops, you need to speak up a little bit.
Hello. Is that
Yep,
better?
I hear you, yes.
Y versus T would be half of a parabola, like this. V sub Y versus T would be linear, and A versus T would be constant.
All right, and so the A versus T, so when you did the V sub Y versus T, did you have that sloping upward or downward?
I guess it would be, it depends on your perspective for how the column is set up.
So if we use these numbers here on this graph, which has now been made sort of messy by my scrawling, what would they be?
A negative slope.
All right, so Let's look into that, because I took, this diagram from the book. So we'll kind of jump back and forth here. So you see the first point is going to be 0, 0. So let's just look at, I'll pick the color that's not very easy to see, but just kind of as a marker. So let's just look at that. So 0, 0, there's that point right there. The next one is going to be, oops, I'm sorry, I didn't want to look at that. I didn't stretch my line here enough. We want to look at this and this. So at t equals 1/10 of a second, we're dropping down a little bit. So t is 1/10 of a second, we drop down a little bit. And then t is 2/10 of a second, we drop down more. And there's that. And then 3/10 of a second, we drop down even more. So the movement to the left here on the horizontal axis is equidistant, but the movement on the up and down axis, the vertical axis, increases as time goes by. So that's going to be the parabola that Jared described. It's going to look like this. The velocity versus time graph, we can look at that a couple different ways. We can think about that a couple different ways. One of the ways that we can look at it is, let me pick another color here. Let's take this kind of orange color. So now we're going to look at these two columns, the velocity and the time column. So here, every 1/10 of a second, we advance to the right on the horizontal axis. We're advancing down, but this time we're advancing down the same amount. So as Jared said, he talked about that the graph's going to look like that. A constant slope means for every step you take over, you take the same size step down. Not the same size as the step that you took over, but the first step over, you take a step down, and whatever that step down equals, the next step you take over, you take the same size step down. Or if these were all positive numbers, it would be a same size step up, but they're negative. So you see that. This over means this down, this much over. So we go over this amount, down this amount, over the same amount, down the same amount, and so on. Over this amount, over this amount. So all the little triangles that I draw here are about the same size. Well, they would be exactly the same size, but my artistic skills aren't very good. Here, all the successive triangles that I'm building, you could argue these aren't really triangles because this isn't a straight side, but triangle-like objects, notice how they get bigger. This is the biggest one. This one's clearly the smallest one. Here, despite my poor drawing, they're all the same, pretty much the same size, and they should be exactly the same size. So that's one way to look at it. Another way to look at it is, and we did this in an earlier video, we know that I'm going to use a different color here. We know that the slope of the position versus time graph is the velocity versus time graph. So if we take the slope right here, so that was the slope at 0.1 seconds. That's a pretty small number, a small negative slope. And that represents a small negative number, -1. If we do the same thing here, the slope at 0.5 seconds, that's a larger negative slope. This is you don't want your car sliding down this hill. This hill, well, maybe you can stop at this hill. It's going to go out of control pretty quickly. And here is a large negative number compared to this one. We recall from before that the slope of the velocity versus time graph is acceleration. And so let's just remind ourselves of that. Slope of y versus t is v versus t. So slope of v versus t, and maybe that's a little bit too simple, results in fact, I'm going to change that word there too. In v versus t graph results in we don't need to be cave people here. A versus t graph. And here it makes sense because the slope right here is a certain value and it's -10, rise. So just remembering from middle school, slope equals rise over run. In this case, rise, it's final minus initial, so -1 minus 0 meters per second divided by t final minus t initial, 0.1 seconds. So -1 minus 0, of course, is -1, divided by 1/10 is -10 meters per second. And again, using that meters per second, that reminds us of the unit. So I mentioned before, this sort of reminds us what acceleration means. It also reminds us that acceleration is the slope of the velocity versus time graph. Whereas if I use meters per second squared, that doesn't really make sense as a slope unit. That doesn't really fit my first thought of what is rise over run. So that was for a ball that was dropped. Actually, I'm going to be bold here, and I haven't actually tried. I practiced it once, but I haven't tried it yet. Ooh, I don't want to do that. Actually, maybe, yeah, I'll do the application sharing. Let's see how this works. So I'm going to show a ball toss, and this is not going to be anything revolutionary. You can see from the time here, it's only going to be 12 seconds. It's just a person tossing a ball straight up in the air. It's going to be in slow motion. And show you the motion. And what I'd like you to do is to think about, and if you want to if you got note paper in front of you, just quickly sketch what the y versus t, v sub y versus t, and a versus t graphs would look like. Now, not just for a ball drop, but a ball tossed straight up and then falling straight back down. So nothing terribly exciting about that. While you think about that, I'll just quickly sketch something here that will not nearly duplicate the representation, but we had a person kneeling down, tossing the ball, and they toss sort of a greenish looking ball. So we use optic yellow, but yellow won't show up very well. So they toss the ball. And the ball changed shape apparently. And then the ball, so ball goes up, ball comes down. Just like the tide comes in, tide comes out. Bill O'Reilly doesn't know why that happens. So ball goes up, ball goes down. What would these graphs look like? So Jared, any idea? You could do your special hand motions again.
Can you hear me?
Yes, sir.
Yes, I can hear you.
So for y versus t, is it okay if I do a sketch?
Yeah, you can actually, let's see, you should be able to see it here. You should have be able to control the whiteboard. There we go. Well, how'd you do such a straight line? Oh, your skill. You're going to be teaching the class next year.
Okay, so y versus t, is the parabola. Like that, but better. And then for velocity, let's see if I can. Oh no. Okay, I messed that up. I'll do it. Okay. And then the next one. E sub y to t. It would. Oh no, it's not. It's a different kind of problem. Whatever. That's right. I did. Here we go. Something kind of like. Should get this class. So it's kind of like the flip flop of the position parabola, because it has the most speed when it is first tossed and then stops at the top and then comes back down.
Okay.
And I'm working on my last one. This is acceleration. I don't know how to do sub y. So
That's okay.
a little longer. This one, acceleration, would be the one I'm having trouble with. Okay, so it starts with getting faster, and acceleration drops at the top, and then would it be another parabola like the first one? This is the one I'm having trouble with.
Yeah, so let's, thanks for giving us input here. That's really good. So let's think about the whole slope issue, because remember when we go from this graph to this graph, the slope of the position versus time is the velocity versus time. And then when we do this, the slope of the velocity versus time is the acceleration versus time. So one thing to think about is when you take the slope of something, let's go back to the straight line. I'm sorry, not the straight line, but the dropping. And this is pretty busy here because it's got all my sketches on it. But the first one was, as you said before, half a parabola. But then when we went to the next level up, that one sort of flattened out. It's still angled, but it's straight, so maybe it's straightened out. That'd be a better way to describe it. And then when we went from velocity to acceleration, then it flattened out. So I know this is not, you folks are not taking a calculus-based class, but I know there's some people who have taken calculus before, maybe in high school. But one way to say that, so when we said before the slope of the position versus time graph is velocity, so if we use calculus, and again, I'm not going to be quizzing you on calculus, but might help put things together, and I know almost everybody's heard these terms. So the velocity is the derivative, the time derivative of position. So that's using calculus. If we use algebra, that is really the delta x over delta t that we've talked about. And then there's the same transition for acceleration. Acceleration is dv dt, or delta v over delta t. So when we go from y to v and v to a, that's telling us we're going to want some sort of straightening or flattening happening. So let's look at this. So first off, I agree with this y versus t graph. So the ball gets higher, and it's getting higher quicker at the beginning of the toss, and then goes up to the top, and then at the end of the toss. If someone were to be, a taller person were to stand here, it'd be easy to grab the ball here because it's changing its motion really slowly. More difficult to grab the ball down here, although just for a 1 meter high toss, that's not going to be a big deal. So yeah, this one, so I agree with this one. So with this in mind, this is telling us that this is saying, okay, at the beginning, I'm going to have sort of a large positive slope. If we just take the tangent of the graph like I did right here. Here we have a small negative slope. Here we have a larger negative slope. So here we have a large positive slope. Here we have a smaller positive slope. Here we have an even smaller positive slope. At the very top, we have zero slope. So that kind of matches this right here, and it's going to get down to 0. When we go on the flip side, though, right after we have 0 slope at the top, now we're starting to get a small negative slope and then a bigger negative slope. So instead of turning back upwards, what Jared actually sketched was sort of the magnitude. He really drew a speed versus time graph. Here on the downward trend, we're going to have negative velocity, because if we define this as positive velocity, then we need to define this as negative velocity. So we're going to have points down here, and Jared uses that voodoo magic to make a straight line. I just cheat and make my points bigger like that. So with this in mind, if you agree that my jump from position to velocity is right, then you know for sure that this is not going to be the proper transition here. So now we've got a uniform slope throughout. So here, slope is uniform and negative. So a slope that's uniform and negative would be, and let me just use, no, I'll use the same color. I should have used a different color for that. It's going to be this right here. So I'll use black to extend Jared's up and down axis. So I'm going to be using sort of a value word here that you could quibble with my use of that word. But the graphs look simpler as you go from position to velocity to acceleration. My writing here doesn't look very simple. From velocity, from position to velocity to acceleration. Yeah, Jared, you had a question?
Hello. There we go. Okay. So for this acceleration one, would it just be, let me see if I can change the color on this, two, like, lines? I'll just draw what I'm thinking now. I think I did it. One here, and then when the ball stops, it kind of jumps down here to the blue line. And then it changed like that, kind of discontinuous, I guess is the word. I've taken calculus before, but that wasn't very good. So,
sure. For this motion, no, it would not be discontinuous, and let me talk about that in two different ways. First, I'll just talk about it the mathematical way, which probably you won't feel 100% good about, and that's certainly fine. So I'll talk about it another way as well, a more qualitative way, and that's more of a story. So for this, the mathematical way, this velocity versus time graph is just a straight line. This is continuous. So the slope, I'm just going to arbitrarily pick some sections here. So the slope of this section is going to be whatever it's going to be, and we didn't get any numbers from this. So this is going to be, say, -1 meter per second. So -1 meter per second for each second over. And actually, since this is actually based on a real ball being tossed, that's a head slap. I'm going to slap my head for what the dumb thing I said. Since this is based on a ball being tossed, then this is going to be a slope of -10 meters per second. So for every second we move over, we're dropping down -10 meters per second. Even across here, for every second we move over, we're dropping down by 10 meters per second. So since this is a continuous line right here, this blue line that I drew, then the slope is also going to be continuous, and that's going to be at -10. And if this is going to be in units of meters per second. So you might say to yourself, well, that, okay, I can kind of see how that works mathematically, but I'm not sure how that works otherwise. I should have, let's see if I have, I think there's a, so there's a blank slide here. So let's look at the ball again. So we're going to draw our person, and I should draw over here. So we're going to, person whose knees go the other way. It's a horse. It's half a horse. So they are going to be tossing a ball, which is better than tossing your cookies. So let's do that. And I'm probably not drawing this perfectly well. So this is the upward part, and then we're just going to kind of shift over to this. So let's take this part just before it reaches the top and then just after, because that seems to be where the trouble lies, right? So, oops, next one. It's that sort of that top part which seems to be discontinuous. So let's just make up a velocity here. Let's just say just before the top it is going at positive, and let me get this right here, 0.5 meters per second right here. So over here Let's see, do I want 0.5? Yeah, that is good. And so this is going to be velocity equals negative 0.5 meters per second. And so this is going to, so we're just looking, so this is going to be we're only considering just this teeny part of the motion right here. So that's going to be V0, so V initial, and over here is V final. And let's just say that that transition here happens in 1/10 of a second. So we know that acceleration equals V final minus V initial over delta t. And the book, I should use the book's nomenclature, say V final. So they like to not have the subscript there for final. So here we're going to have, now we're just going to plug in. V final is negative 0.5 meters per second minus V initial, which is 0.5 meters per second divided by 1/10 of a second. So negative 0.5 minus 0.5 is negative 1 meter per second divided by 0.1 seconds. So they're going to get negative 10 meters per second per second. So even at the top, of the motion, there is a negative acceleration, or a downward, let's just say downward acceleration. And then we can ask ourselves, well, what if, and let's put that in a different color here. So what if the acceleration at the top was equal to 0? So what does that mean? Oops, sorry, I took my pen away, left the cursor there. So if acceleration is 0, and someone can either verbalize this or put it in the chat, what does that mean? And think back to this equation. So yeah, Jared typed in the ball would stop moving because there'd be no, so that means delta V would be 0. Oh, and that means, as Jared said, very everyday life-ish, not physics formulas. The ball would stop. And not only stop, it would stop and it would stay stopped. Because in this scenario, what is changing? If the acceleration is 0 at the top, you could say, well, okay, it's only 0 at the very top. Once it starts to come down again, then the acceleration is not 0. But if the acceleration was 0 at the top, and we know that just before it gets to the top, it's not moving 0.5 meters per second, it's moving 0.000001 meter per second. So it's pretty darn close to stopped right there. And then it gets to the top, its velocity is 0 at the top, but just because the velocity is 0 doesn't mean the acceleration is 0. So let's go back to, so this was what we speculated. And this is a diagram that I cut out from the book, copied and pasted from the book, except this was from a sample problem this, from the sample problem, there's a little bit different situation. So ignore that. Actually, that's probably the worst looking word, ignore, I've ever seen. So if you look at this, you see that we have the straight line for the velocity versus time, but a downward slope, and then we have that constant negative 10 meters per second per second. So questions or comments on that, either verbally or in the chat? So let's go over, for sure, one sample problem. And I'm going to do two parts of this problem here. So calculate the displacement and velocity at times 0.05 seconds and these other two, and then 2 seconds for a ball thrown straight up with initial velocity of 15 meters per second. So we have our person, and they're throwing the ball. So initial velocity 15 meters per second, so it's going to go up. It's going to come straight back down. So V0 equals 15 meters per second. It says take Y0 equal to be 0 meters. Since this is not a problem that depends on time of day, we'll let T0 equals 0. Doesn't matter if we're talking about a half a second after 8 in the morning or 8 at night. Maybe at night it's too dark for us to catch the ball, but that doesn't matter. And now we want to know, so calculate displacement and velocity. So we want to know what, so the unknowns that we want are velocity at 0.5 seconds, y at 0.5 seconds, and I'm just going to do the last one. So velocity at 2 seconds and y at 2 seconds. And what we're not given here directly in the problem, but we also know, so these are our knowns. And these are the knowns from the problem, but there's one other thing that we know. We also know that A equals negative G if we take our axis to be the traditional XY axis, where up is positive Y, and then right is positive X. So for the position, we can use y equals y0 plus v0 y t plus 1/2 a t squared, where a is equal to this negative g. Yeah, Jared, you had a question?
Okay, so we have 3 equations for velocity equals v sub 0 minus gt, but I'm kind of concerned about the other two, but yeah. So when do we know when to use y equals why is there, let's use the second one or the third one? Like, what's the difference between the two?
Sure, great question. Since I'm on this, let's just talk about that. So notice that this one includes time, but it doesn't include velocity. So typically, when you know time, or you need to know time, you're going to use that one. This is one that you'd use, so let's just kind of focus on time. So this one, if you don't know time, you're most likely going to use this one here. Notice that this one, also this one's useful, the middle one, if you don't know the final velocity, because this doesn't have final velocity in it. This lower one doesn't have time in it. So the first part of the question was we toss a ball up in the air, and after half a second, what is its position and what is its velocity? So we don't want to find the velocity after a half a second using this equation here, the middle one, because it doesn't have final velocity in it. We don't want to use the bottom equation to find the time because it doesn't have time in it. We know G, we know the positions, and those fit into both of these, right? The middle one has the positions and the acceleration. The bottom one has the positions and the acceleration. They both have the initial velocity. This one has final velocity, so we'll use that to find final velocity. This one has, oh, actually, I'm sorry, we don't know the positions, we know the times. So in this problem, we'll use the bottom one to find the velocity because we know everything on the right-hand side of the equation. For the first part, we'll use this one because we know it's a half a second later, we know G, we know V sub 0. So typically, your first choice is to look for an equation that includes everything you know, and there's one unknown, and that's the unknown that you're looking for. So this middle equation has one unknown, that is y, and y is what we're looking for at a half a second. So then we can just plug in here y0 is 0 plus v0 is 15 meters per second times 0.5 seconds minus 1/2 9.8 meters per second times 0.5 squared. So let's break this down a little bit, and then we're just going to plug in, and I'll look at the final answer, which isn't that exciting. 5 point, and you could so look at significant figures here. They've given the time to 3 significant figures. I plugged in 9.8, which is really 2 significant figures. To 3 significant figures, you could use 9.80. There's fluctuation throughout the Earth, so I think standard use is 9.80. Different parts of the world, there's going to be slight variations. The top of a mountain is going to be a little bit different. If you're right above a mine with a lot of dense metals in it, and you're standing above it, acceleration due to gravity is going to be a little bit greater. So let's sneak in another significant digit here, just to match what we have, 2.8. Oops, that's an ugly looking 8 meters. And just to quickly check the units here, meters per second times seconds, you end up with meters. Meters per second times seconds squared. You end up with meters, so that works out. So if you look at this, just to sort of see what the formula is telling you, if there was no gravity, if gravity was 0, it's a pretty ugly G. So if G equaled 0, or very close to 0, let's say we're standing on a very small asteroid, well, G wouldn't be 0, but it would be really, really tiny. That means we'd be subtracting off a really, really tiny number, which means that we would have just this number. So if gravity was 0, y would equal y0 plus v0 t, which in this case would equal 7.5 meters, 15 times 0.5. So you can see that gravity is taking away some of the position change, if you want to use kind of informal colloquial language, taking away some of the position change every 1/10 of a second. So because of gravity, the ball is not as high as it would be if we had 7.5 here. And for velocity, I'm actually not going to, I'll just write down the equation that we're going to use. So for velocity, v squared equals the initial squared minus 2 times g times y minus y0. And if we plug the numbers in here, so the same sort of thing, v0 squared, 15 meters per second squared minus 2 times, what we just solved for, 6.28 meters. We could have also used v equals v0 minus gt as well. And in fact, when I was looking at my solution that I have here, that's what was used. But when I didn't look at it while I was working on it, and since we went back to visiting those equations, we did that. So actually, since we kind of have an understanding with this, I'm going to go ahead and, so this was just going to be space. This is the same problem. This is just going to be extra space to work on it. But instead of doing that, since we're at 1:30, and I would like to just talk about this one a little bit here. Calculate the height of a cliff if it takes 2.35 seconds for a rock to hit the ground when it's thrown straight up from the cliff with initial velocity of 8 meters per second. So let's just draw this. So here's our cliff, and here is our person. They're tossing the ball. So initial velocity of 8 meters per second. So v0 equals 8.00 meters per second. And again, it doesn't matter the time of day for this. So we'll just say that t0 equals 0. If it mattered the time of day, maybe we start our clock 1 hour in, and then it's going to land 1 hour and some odd seconds later to hit the ground. So t final, we don't know that. Okay. Oh, I'm sorry. We do know that. What we don't know is some other aspect. So we know the t-final, I apologize, is 2.35 seconds. So you might say to yourself, man, well, that's not a lot of information. So we need to do a couple. We do have one more bit of information, and then there's something that we haven't actually incorporated yet. But we do know the acceleration. I just wanted to make my little subscript 0 here a little bit better. So we know the acceleration is negative 9.8 meters per second, and that is predicated on using the traditional up being positive, down being negative. So now we need to figure out where we want our 0 to be. So, oops. So we have a decision to make. And we can look at what happens depending on the decisions here. So y0 equals, and calculate the height of the cliff if it takes. So we want the height of the cliff, and then y final so we need to decide where we're going to have the 0 of our axis. So I happen to draw this up here, but we can move this around here, and I should figure out how to make all my pictures go together. So we need to decide where we want our actual origin to be, because that's going to decide here what we say is y0. So it doesn't really matter. I kind of like to have my number lines start sort of where it makes sense. So what I would do is, oh, that's interesting. I'm going to delete that. That's kind of dumb. So we'll go back to actually drawing. That was a waste of time. Should have just redrawn it again. So I would prefer to say that the y final here, when it hits the ground, is equal to 0, and y initial is what we don't know. So we are also assuming, so we're assuming constant velocity. We're also assuming that the person who's tossing the ball is releasing it right at the edge of the cliff. And a normal person's probably going to be releasing the ball at about chest height, not down at the ground. If we want, we can think about that afterwards. So we know A, we know delta t here, or we know what t is. We know v0. So going back to the equations that Jared asked about before, we want to use the middle equation here. So y equals y0 plus v0y t minus 1/2 gt squared. So y final is equal, so that means that y initial equals So equals y minus v0y t plus 1/2 gt squared. So if we plug in our values here, y, and what I said y final is, oops, should just be considered, the book uses that, they don't use the final nomenclature. Alrighty, so I'll just finish this up. I see Jared needs to get going, but I'll just quickly finish this up and you can watch the recording. I'll just take another 5 minutes or so to finish this. So y is 0 minus 8 meters per second times 2.35 seconds plus 1/2 9.8 meters per second times 2.35 squared. Sorry, I kind of squished things in there. So 2 issues. One is, why did I put in 9.8, not negative 9.8? Well, I accounted for, if I use that formula, I accounted for the negative right here. And another, seems kind of weird, why am I subtracting this off and adding this over here? Well, the glib answer is because of the algebra here. When I moved these two things over to the other side of the equation, we subtracted v0t and we added 1/2 gt squared. But it makes sense that these two terms, the 8 times the 2.5, are going to be opposite signs from this. And since the ball is going down here, the second term is sort of the term that's moving the ball downward. This is the term that's moving the ball upward. So since the ball is going to end up at a net downward, it makes sense that that term which is moving the ball downward, that's going to be about 20 or so, 8 times 2.35. This is going to be a lot bigger here. Not a lot bigger, but it's going to definitely be a bigger term. And if we plug all this stuff in, we come up with 8.26 meters. So a ball is thrown straight up with an initial velocity of 8 meters per second. It's going to take it's going to fall in 2.35 seconds. That must mean that the cliff is 8.25 meters high. The top part of the ball, so that means that this is 6 meters. We know the ball had a greater trajectory than that. The ball went like this, and then it went down. So this overall height, this is obviously going to be greater than 8.26 meters, but that's okay. We don't even need to worry about how high up it went when we figure these out, because these represent unique points, and that also reinforces the fact that y or x or y0 or x0 represent positions and not displacements. If we're worried about displacements, yeah, then we'd have to worry about this upward displacement and then the downward back to the original toss location, and then from the toss location down to the bottom. So let's go to the next part here. So now how long would it take to reach the ground if it's thrown straight down with the same speed? So now, oops, I don't want to use that color. I won't do the drawing again. But now, V0 equals negative 8.00 meters per second. Now, T is our unknown, but we do know Y0 is that 8.26 meters. Y is equal to 0. And we're saying that T0 equals 0. So we know the initial. We don't know time. We know the two Y values. So we can still use Y equals Y0 plus V0 YT plus 1, oops. I guess I didn't need there. We can keep it like that. That's convenient. Minus 1/2 GT squared. So we don't know time, but we're going to need to use the quadratic equation. So if we use that, make sure I get that right. So that's going to be, first off, we need this to be 0 on this side. So 0 equals Y0 minus Y plus V0 YT plus negative G over 2 T squared. So we can plug negative 8 in, so that means we're going to get here. So that's, remember the quadratic was negative b plus or minus square root of b squared minus 4 AC over 2a, where the A, B, and C come from AT squared plus BT plus C. I should have drawn that in a different color because that's different from the parameters here. So if we plug in the numbers, we're going to get negative 8.00 meters per second plus or minus square root of square root or square root. Is that one of those words that depends on where you grew up? You're going to say it differently. I grew up in the Midwest. So that's going to be 4 times 4.9 meters per second, because we have a minus here and the negative here turn out to be a positive. I probably didn't need to skip that step. Times 8.26 meters, all that divided by negative 9.8 meters per second. And we are going to get two values, 0.717 seconds and negative 2.35 seconds. So we can address this two different ways. We can say, well, there's no such thing as negative time, so clearly this is the answer. But this has meaning as well. So what is the negative 2.35 seconds? I wasn't very strategic in my time, but let's just quickly draw this. So here's the starting point, and here's the ground right here. So this took 0.717 seconds. What the negative term is, because the quadratic is assuming a parabolic trajectory, or in this case, it's a squished parabola. So what that is assuming, there's our 0.71, but in order for something to be moving at 8 meters per second downward at that height, it would have had to have been thrown 2.35 seconds earlier from the ground. So somebody throwing the ball from the ground such that right here the velocity was negative 8 meters per second, that would have happened 2.35 seconds. That would be that trip. So about 1.6 or so seconds before here. So if you're standing on the cliff and you throw the ball downward at 8 meters per second, somebody else would have to throw the ball upward with an even greater velocity such that it reached your position about 1.6 seconds later. All right, well, thanks for listening. For 15 extra minutes of listening, and we will see you later.